Okay, I just wanted to work out one more problem with work and energy just so we can get this down right here. And you remember, this is the one equation that would answer every single question we have. Remember, this is related to the height of it. That's the MGH term, MGH. This one is related to the spring, the stretching or compressing of the spring, which is 1/2 ks squared. This has to do with the velocity, which is the 1/2 mv squared. And so that was the total energy at the initial point right here. You had also this same three terms at the final point right there. And normally they would be equal unless you lost energy out of the system. Well, how could you lose energy out of the system? If you had friction right here, you'd lose it out. Or if you put your hand into there, you could either gain or lose depending on whether you help it or hurt it. So this was our one equation right here. So let me just write out these equations between different points. Let's say we write it out between A and B right here. Just this equation right here. Now, the only place I have friction in this problem is right here. There's the only spot I have friction, and my hand isn't in this problem anywhere. So this one's going to be 0 throughout the entire problem right here. So really, I'm just asking about these points right here. So if we go between A and B, and this thing starts, this thing was compressed a distance s, and then just released. So it started from rest. This thing took off, goes around the loop, comes back around, and eventually runs that rough surface and stops right there. So it's stopping right there. Okay, so first, let's look at it just between A and B right here. So between A and B, first of all, I'm going to call this height 0 right here. So this height would be R, and this height up here would be 2R. So there's no potential here. We do have spring energy, so we're compressed S, so the spring has 1/2 ks squared. So we got 1/2 ks squared. It's not moving there, so that's 0 right there. We have no friction between here and here, and there's no hand force between here and here. So this is the entire left side right here of the equation. Now, when we got to here, we do have some potential energy. We're above the ground. We're R up above, so we got mgr. And then there's no spring. The spring is back compressed right there, so it has no spring. But we do have some kinetic. You have some velocity right there, VB. So we got plus 1/2 mvb squared. So that would have been the equation between here and here, right here. If I knew S, and I knew R, I could find VB right here. Remember, if I know VB here, I could find the inward acceleration, because the inward acceleration is VB squared over R, so I could get it in case I needed it right there. I could even get the normal force, because the normal equals mvb squared over R right there. So I could calculate all that stuff right there. Well, suppose we were to go, I could go from B to C, but we'll just go, how about just from A to C right here? So we'll go from A all the way to C. I'm assuming that it doesn't fall inward, right? It's going fast enough so it doesn't fall inward. Well, the total energy at A is still the same. It's just this. It starts out, well, with spring energy, nothing else right here. But over here, now we have more potential. We have mg2r, plus we have some kinetic, 1/2 m VC squared. Right there. So if we wanted to find out the speed at C, we could use that right there. Or we could have worked it the other way. We could have said, remember, we said the minimum speed at the top is when the normal goes to 0. So we could have said, let the normal go to 0 up here. If your normal goes to 0, the only force you have on it is mg. And if you looked at the sum of the forces inward, you just have mg, and that equals mvc squared over r. So you can cancel the m's, and so you could say, if you wanted to go at the minimum speed at the top, you could say vc equals the square root of gr, and we could have plugged that down into there, and we could have said, what does s have to be? So you just make it over the top right here. But if I would have said that right there. Okay, so we looked at it between A and C right there. We could look at it from A all the way to D right there. We look at it from A to D. Well, remember, the energy at A is still the same. It's still just all spring energy. 1/2 Ks squared. Now, this loop doesn't even matter. We don't care what happened in between. We're just looking at the two endpoints right here. So, there's no gravity at the end. There's no spring at the end. It's all kinetic at the end. So this is equal to 1/2 mv sub d squared. So if I knew what S was, I could find V sub D, or vice versa, right there. Or I could go from A all the way to E. A and E. I don't have to always start at A. I can go between any 2 points I want, but I might as well start at A. That means the left side is always the same. 1/2 Ks squared. So that takes care of these three. But now I do have some friction right here. I'm going to have some friction right here because I'm going all the way to E. So it's minus the friction times how far it slid on that rough surface. So it would be minus the frictional force times D. Okay, and then over here, this is 0, that's 0, and that's 0. So this is equal to 0 right there. So I could have calculated how far it slid as long as I was given, remember, frictional force, this is kinetic, which is mu k n, but we know n is equal to mg, so it's mgd right there. So know how to use this equation between various points, and then you could use other information like this up here to solve for if I wanted to give you a handle on one of the speeds right there. But this is pretty much it for all the homework questions right there. Okay, so